So, good morning, everyone, or good afternoon, or good evening. This will be your pre-recorded video for thermodynamics. So, in this case, we are only going to have an introduction to chemical thermodynamics. So, everything that is already written in your modules will not be discussed here. Solely, I will just be explaining briefly what is thermodynamics and the idea of thermodynamics involving heat and work. Then the other terms will be discussed or are already discussed in your modules, and I will be focusing more on the solution or solving processes of thermodynamics. Please make sure to have your essentials with you. Please have your calculator and of course the values that I gave you, the appendix wherein the values, the thermodynamic quantities are already present, especially for our enthalpy, and Gibbs free energy. There will only be one target for this pre-recorded video, and that is by defining internal energy, heat, and work. So we will start with the idea of thermodynamics. So I will be explaining it briefly. Then right after that, we will focus more on the enthalpy, entropy, and the Gibbs free energy. So defining thermodynamics, when you say thermodynamics, it came from two Greek words, which is dynamic and thermo and dynamic, and they means heat and power respectively. So why does it why does we why do we combine these two words? Okay, these two Greek words of heat and power. Okay, we will know that later on. So in thermodynamics, it's actually the interrelationship of the three, your heat, work, and energy. The goal is for them to be able to have a system that is at equilibrium. When you say at equilibrium, that means they are balanced. Remember, we have the law in chemistry. The first law in chemistry is that there's always a conservation of mass. And that we know, energy is neither created nor destroyed. Hindi po sila nawawala at hindi po sila nagagawa. Thermodynamics tells also chemists if a certain reaction or a certain chemical reaction is possible. Okay, so in here, we will focus more on the chemical thermodynamics part of thermodynamics because this is under general chemistry too. So let's discuss the idea of system and surroundings. So in chemical thermodynamics or in thermodynamics in general, we have always the what we call system, and the outside of that particular system is the what we call surroundings. Now energy can flow into or out of the system. Okay, so it could actually go inside, no, not inside, it will go into the system or outside the system. Okay, and that is, there are two ways in having that, and that would be through heat and work. If your system gain a particular energy, that energy is called internal energy. You can see this in your module. It's actually denoted as capital letter U. So again, there are two ways in how are you going to gain or lose energy, and that is through heat and work. Surroundings could also not just give heat or into the system, it could also have work done into the system. Now, let's have the idea of the law of conservation of energy. So take for example that the surroundings will exert a work that is 300 joules into your system. That means that the system, the internal energy of your system actually increases. So that means there is a positive addition, okay, of 300 joules. Okay, that means that your delta U increases. The internal energy of your system here increases. How about your surroundings? Your surroundings now, on the other hand, will lose the 300 joules. So see, it's just the same energy, It's 300 joules. The only difference is that you have the positive and negative sign. Don't get confused, because in other subjects, when you say positive, there's an addition, and when you have negative, it's um, there's a subtraction. But in other subject, that means that you have, when you say negative, may utang ka pa. Okay, especially in math, it's defined as integers. In here, it's just a it's just a symbol that a particular energy was lost in the surroundings, and it was added in the system. So as you can see, that 300 joules came not just from nowhere. Okay, galing siya sa surroundings na na-transfer kay system. Okay, and para mas maintindihan nyo, let's have an example that is live application. Take for example, you sell your laptop for 50,000 pesos. And of course, you wanted to have a bank transfer in your account. So, if, take for example, I will be the one to buy your laptop, that means that in my bank account, there should be a deduction of 50,000 pesos so that I can buy your 50,000 pesos worth of laptop. While in your bank, okay, in your bank account, there is now an addition of 50,000 pesos. That means you gain the 50,000 pesos and I lost the 50,000 pesos. What does it mean? That means that for something to gain, someone should lose. That is the idea of thermodynamics, especially in heat and work. Now, since we're already done discussing what is a system and what is its surroundings, let me introduce to you to the three different types of system. We call it the open system, the closed system, and the isolated system. So all of them are systems. So these are the three types of systems. So in open system, matter and energy could actually go in and out of the system. Both of them, matter rather, and energy. Example of matter in this case is oxygen gas. So in an open system, matter such as oxygen could actually go into the system and out of the system. For the closed system, matter such as oxygen, okay, it cannot get into and out of the system in a closed system. While energy, of course, since energy, it could actually go into and out of a closed system. How about isolated system? For isolated system, both matter and energy could actually cannot get into and out of the system. That is now the isolated system. Now, what does it mean, or what does it imply? That implies that in an isolated system, its mass is actually fixed. For the reason that matter and energy cannot get into the isolated system. Okay? What is another constant here? Since you cannot have a matter and energy getting into and out of an isolated system, that means that the internal energy of your particular isolated system is already fixed as well. It's already constant because you cannot change it, because matter and energy cannot get into and out of an isolated system. So that is the difference between the three types of system: the open, closed, and isolated system. Remember as well that if your Q is positive, that means that the system absorbs energy, and that means it is endothermic. If your Q is negative, that means it releases energy, and that means it is exothermic. Okay, now let's talk about the enthalpy change. So when you say enthalpy change, of course, it's a change. So that means you need two values. You need the before and after for you to be able to know what is your change in enthalpy. Is the heat change accompanying a chemical reaction? So we know that when you say enthalpy, we are dealing with heat, which is one of the ways on how are we going to get to gain or lose energy in a particular system. And that is through enthalpy. That is what we mean by enthalpy. It's heat. And it is denoted as letter H. So when we are talking about the change of enthalpy, of course, that would be delta H. So the enthalpy change tells the amount of the heat absorbed or evolved during the reaction. Okay, so for the formula of the change of your enthalpy, it actually differs on what are we looking for, and especially on the given in a certain problem. Now, if the problem gives you already the chemical equation, okay, of the reaction, wherein it was given that it is in a 25 degrees Celsius, okay, that's a constant value, then you can use the appendix that I've given you, wherein there are the values under delta S, okay, sorry, delta H for the enthalpy. So kindly get that appendix. We will be needing that in our next problems. So for the formula of your enthalpy, that goes with the change of your HF prime is equal to the summation of your N to N HF prime products minus the summation of your M to M HF prime of reactants. So this is not just that's why it's a summation, because we are talking about the different reactants that you will be needing and the different products that you will be produced in a particular reaction. Now there are cases wherein you have two reactants, then you have only one product. There are also cases wherein you have one reactant, then you will have two or three reactants. So the main idea is that we need to have the total heat formation of the products subtracted to the reactants for you to get the change of your enthalpy. Now, there are also cases wherein the products will be three or more. So all you have to do is to add everything, to have all of their, um, to find every enthalpy values under the appendix or under the table in the appendix that I gave you, then that would be your product side. You subtract that to the total product of your reactants, then there you will get the delta prime or the delta HF prime value of your enthalpy. Doble na. Anyway, so of course, it would be a lot easier if we are going to identify what are these sum. So I'm just gonna have the example wherein you have the chemical reaction A plus B yields to C plus D. Take for example, you have that kind of chemical equation, but it's not just limited to that. Again, I've mentioned a while ago, there are cases wherein your reactant is 1, 3, 4, and so on and so forth. Then for your product as well, you could also have 1, 2, 3, or more. Now, in this case, if you're going to use this wherein you have two reactants and two products, remember that we have always the coefficient, the number of moles before a certain compound that signifies how many moles are involved in the chemical reaction. And those are actually denoted by the small letters. Okay, so you now have your number of moles per reaction. So what would be the formula if you have this kind of chemical reaction? Then that would be delta HF prime is equal to the bracket. All you have to do is to have your numerical coefficient multiply to the HF prime value of your reactant product C, plus the numerical coefficient of your second product multiplied to the HF prime value of your product D. Subtract that one to the A, where sorry, to the sum of the products of A and the HF prime value of A and B, HF prime value of B. Now, what are these HF prime value that I am talking about? You could see there these values. So, of course, these letters that you have here, C, D, and A, as well as B, you have to replace that with a particular compound if you are already given with an example compound or an example chemical reaction. Then that would be the time that you're going to look for the values in your appendix so that you could use that value in solving this formula. Actually, this is just very easy. Sobrang dali lang talaga niya. All you have to do is to follow, of course, the formula, and medyo wag kayong tamarin na magsulat because I know this is too mahaba. Okay? Lagi yung process natin. But this is one of the easiest part of chemical thermodynamics. Okay, now let's have one example involving enthalpy change, or the solving for enthalpy change using the formula that we have just a while ago. So let's take, for example, we have the change of the water from gas form into liquid form. So we know that for you to be able to change phase from gas to liquid, you need to make sure that you remove energy, kinetic energy in particular, in the molecules of water for them to be able to be slowly moving na, for them to become liquid in phase. So because of that, we could actually hypothesize that there should be a release in energy for you to be able to have this chemical reaction. For you to change gas to liquid, you need to make sure you lost energy, you remove energy. So we are expecting that the delta H value that we should have here should be negative. Because when you have a delta H value that is negative, that means there is a release in energy. Well, if your delta H is positive, then therefore there is an addition of energy. So take, for example, we have this one. You might be needing your appendix by this time. The one that I gave you, please make sure that the one that I gave you will be the one. Please make sure that you used the appendix that I gave you, the table of values that I gave you, so that we will have the same values. So for water in gas form to change in a liquid form, of course, we need to solve for their delta H. So your delta H here is equal to HF prime rather, will be equal to C. Then you have the HF prime value of C plus D, HF prime value of D minus A, HF prime value of A plus B, HF prime value of B. So there, that would be your formula. Now remember, we need to, in this formula that we have, it is just true if you have AA plus B, C, and D. And as you can observe, you only have one reactant and you only have one product. So what are we going to do in the other values? Well, of course, since wala sila, that would be 0. So in this case, you only have one product and that is C. Make sure that the equation is balanced before you proceed in solving. So that would be 1. That would be HF prime value of your H2O in liquid form. Please make sure to write everything because if you will not, you'll get confused. So sometimes, iba yung values na makukuha mo. Instead of having an energy release, your answer is an addition of energy. And that, in enthalpy, of course, that is incorrect. Okay? Then, plus, since we don't have D, a second product, that would be 0. Minus, you have A, 1, then the HF prime value of your H2O in a gas form, plus, of course, your B, which is, there's none, so that would be 0. Then all you have to do is to look for the value of your HF prime, H2O liquid in the table of values. And in that case, that is negative 285.8 kilojoule per mole plus 0 minus, you have 1 times the HF prime value of your water in a gas form that is negative 241.8 kilojoule per mole, of course, plus 0. Then you now have all you have to do now is to solve and to have that in your calculator, and you will get the value of your delta HF prime as negative 44 kilojoule per mole. Since the value here is negative, therefore there should be a release in energy. And recalling your your lesson in kinetic molecular theory, we know that for you to change a gas phase water into a liquid phase water, you need to remove kinetic energy from their molecules for them to move slowly compared to that of the gas form. And there you now have the liquid. So therefore, our answer is definitely correct. So that is how are you going to solve for a thermodynamics problem under enthalpy given a chemical reaction. Now let's have another example with regards to enthalpy. So you have here a solid zinc added to a hydrochloric acid and aqueous solution producing zinc chloride and hydrogen gas. Now let me just give you anong tawag na to? A heads up that not everything or not every chemical reaction that we will be using are actually true. That means there is a possibility that it is not possible in real life situation. So that means that what we are having here is a hypothetical chemical equation. So we are just using this one for the sake of our discussion. So in here, of course, we need to write down first your formula, and that would be delta HF prime is equal to the C multiplied to the HF prime of C plus the HF prime of D minus A HF prime of A plus B HF prime of B. There, you already have the formula. Next step is to determine if your equation is already balanced. So as you can see, we have one zinc, 2 chlorine, and 2 hydrogen as well. So this equation is already balanced. So the next step is to write down what are your numerical coefficients in particular, as well as your different compounds. So that would be 1, okay, and that would be HF prime, zinc chloride, in an aqueous solution, para di kayo maguluhan, plus your D, okay, which is 1, sorry, let me erase that. Okay, that would be 1. Then the HF prime value of your hydrogen gas, okay, minus your reactants, which are 1, HF prime value of your zinc in solid form, plus 2 times the HF prime value of your hydrochloric acid in aqueous solution. Next step is to write down the formulas, or write down the values rather. Now go to the table of values that you have and write down the specific values in every compound. So that would be 1. Then the HF prime value of your zinc chloride in an aqueous solution is negative 502.0 kilojoule per mole, plus you have there 1 HF prime value of your hydrogen gas, which is 0, minus you have 0 as well, 1 times 0 because that is zinc. Then that would be plus 2 times negative 167.2 kilojoule per mole. Then all you have to do is to do the mathematics, and you will get a value negative 167.6 kilojoule per mole. And if you're going to take a look at the value, since it is negative, that means we are releasing energy. There is a release in energy. So that is how are you going to compute for the enthalpy. And that would be all for this pre-recorded video. That is just for enthalpy. Now, there will be a separate pre-recorded video which will tackle the different types of enthalpy, discussing as well what is entropy, discussing Gibbs free energy, and of course the Hess's law. So all in all, we have 4 pre-recorded videos for chemical thermodynamics. So the reason that I cut it so that hindi siya hindi siya mahirap i-export yung video, and hindi siya mahirap i-upload din sa YouTube, just like what I encountered in the previous pre-recorded videos. Medyo mahirap siyang i-record. So that would be all for this pre-recorded video. Thank you so much for listening. And if you have questions, just comment it down below so that I can read your questions, and I will be answering that during our synchronous discussion. So this is Miss Arlie. I hope you have a great day. Bye everyone.